Okay, that was our student data track software winner. The very entertaining, learning about Kabaddi. I'm not sure I understand. All right, next up we have, so yeah, you really need to pay attention closely for these next two talks because you're going to vote on these next two talks during the following break. Audience vote participation, because we're going to have our two methods track finalists in our student division of the reproducible research competition. So first up, we have Boulder2Vec, modeling climber performances in professional bouldering competitions with Zeke Weng, University of Toronto, Victor Howe, University of Toronto, and their group partner Ethan Barron, who is unable to make it. So Zeke is second-year student at University of Toronto studying computer science statistics, and Victor is a third-year engineering student at UT majoring mathematics, statistics, and finance. This UT group has had some pretty good success in various data science competitions in the past, so let's see how they do this time. Let's thank them for joining us.
All right, thank you for the kind introduction. Once again, I'm Victor.
I'm Zeke, and we are here on behalf of the University of Toronto Sports Analytics Group.
Yeah, so we're going to present our project on how we can get better insights into the world of competitive bouldering. So first, can I just get a quick show of hands? How many of you know what bouldering actually is? Yeah, okay, so how many of you ever gone bouldering? Yeah, so as we can see, it's like a pretty popular sport, for the tech bros especially. But it was even featured in the Olympics recently, 2020, 2024. And in addition to that, it was featured in the International Sports Climbing. Yeah, so we got our data from there from 2007 to 2022. And I think the most straightforward question you can ask about bouldering first is, well, what's the probability of success of a certain climber? Right? So I think the most straightforward way to answer that as well is with a logistic regression model, just to think about okay, can we actually model how successful a climber is on any given problem, which is just like a route basically. So yeah, first we had to gather some consensus for what would be the top climbers. And here we kind of made a list of the top 5 women's climbers or female boulderers over the past couple of decades. And this list was compiled just through a bunch of sources online, GBT, Claude especially. But then we fit our logistic regression model, basically giving a coefficient to each of these climbers. And here are the top 10. As you can see, there's a pretty good match between who we think should be the best climbers and who we actually see in the model. And here again, the highest coefficients. For example, Yanya Gombre, she's basically the consensus GOAT of women's bouldering. So it's nice to see her at the top. But this leads us to some other questions that we have to talk about. So the limitations of logistic regression, when is a climber or why is a climber good? When we see a ranking like this, we don't really get much information about what makes them so good, right? We just kind of see their ranking, their points, but we want to know more about them. What is different about their style or how they solve a different climbing problem that makes them so good? With logistic regression, we get a single coefficient for each climber. And this gives us a okay accuracy and a very general prediction that lacks more nuance into how that climber works and how they actually succeed on their problems. In addition to that, something that I should mention is that in competitive bouldering, the problems are all unique. This means that if you imagine a competition, for every round of competition, when a climber is about to attempt a wall or a problem, that's the very first time they've ever seen that problem. It's a unique thing. And so they basically have to do a lot of thinking to figure out what their intended moves are. And here in this video, we can see just how important the problem is to predicting climber success. This is Yanya Gombre. She's rank 1, as we can see, or recently rank 1, yeah. Very easily just grabs over and gets the hold. This is Ai Mori. She's rank 3. She's 4 inches shorter at 5'1", and she's trying to reach, but she can't reach the same hold as Yanya. And so she has to get creative. You see, she's putting her fingers on a very, very tiny screw hold in the actual block. And this is what is letting her reach the same point. But you can just kind of like imagine this is so much more difficult than what Yanya had to do, right? And so you can think about how this means we have to incorporate problems into the actual model that we're forming to predict success.
Right. So knowing that we have many limitations for the logistic regression, we thought we need to incorporate more factors into this. So to start, we have problems, and we want to capture the many characteristics of these problems. And to do so, we used a vector. As you can see here, we have many different entries in this vector, and each entry will be known as a latent factor. And along the same lines, we want to capture characteristics of the climbers, their ability to climb, and also their style and perhaps their physical characteristics. And we'll also encode these features in a similar way. And if you see the way that this is set up, and know that our goal is to make a prediction on this problem for a specific climber, if you've taken a basic linear algebra class, you would know that this is very similar to the relationship of a dot product. So after we multiply these out, we get a prediction. So that is the intuition behind our main project. But let's take a step back and actually look at our data and how we got here. So we have data on problems and climbers organized in a matrix. As you can see here, they're sorted in binary fashion, where they either complete the task or they do not. And what you might also notice is that there are empty entries. And this is intentional because not every single climber across the last 15 years has tried every single problem. So our data is sparse, and we have to overcome this sparsity with our model. So if you follow on from before, we know that we need to perform some matrix decomposition. And there's many different techniques out there like CNMF, non-negative matrix factorization, and many other methods. But what made most sense for our data specifically, especially because of the sparsity, we used probabilistic matrix factorization. Now, we can get into weeds of the math behind that, but I'm sure that would be very, very boring for you all. But let's understand why this is a great model and the results that come from it. So first off, the predictions. Do we perform better than the logistic regression? Well, on the graph you can see here, we have plotted the latent factors, as I mentioned previously, from 1 to 5, and also the accuracy on the y-axis to see how we perform. Now, with one latent factor, it's kind of mimicking what the logistic regression is doing by capturing one factor, and they're very similar in their accuracy. However, when we move up to the second latent factor, we see there's a drastic improvement in our accuracy and our results. Now, if we go further along, we see that there is some overfitting as our test data and training data is deviating in their accuracy results. So as a result, we thought that latent factor 2 was the most ideal part and what we will be analyzing further along. Now, these are nice results, but we want to actually understand why and actually identify the characteristics of them. So to start, we took those two embeddings and ran a PCA on them. PCA analysis, or principal component analysis, and we ran that with the correlation matrix for the number of climbs, the probability of success, our LR coefficient, and also height. So as we expected, for principal component 1, we see that's highly correlated with the actual success rate of the climber. And we see that this is kind of in line with what we expect, as that is like telling us how strong the climber is. And what's more interesting is principal component 2. So we see that there's some correlation between the principal component 2 and the height, suggesting that there may be some physical characteristic correlation there. But also it could be because it's not super strong, it could hint towards maybe a bouldering style or something like that. So to further examine this, let's look at a specific example. We see that two current boulderers who are at the top of their game, Do-hyun Lee and Tomoe Narasaki, are ranked 2 and 4 respectively as of today. And we also see that the principal components are very similar because they're very similar in strength, but their principal component 2 is very different. And this is in line with our expectations, and it reaffirms our model because we are hypothesizing that PC2 is picking up on climbing style. And their climbing styles do differ. We see Do-hyun Lee as a more methodical, reserved, and calculated climber, while we see Tomoe as more aggressive, combative, or not combative, but like very explosive in his techniques and often leveraging momentum for his climbs. And that is exemplified through the differences in their PC2. Now we can also look at across all the climbers that we have, and we see that there's a gradient, and you can clearly see that the gradient illustrates the probability of success and how strong these climbers are, as you can see here. And also principal component 2, we see most climbers are close to 0, meaning that they have a very similar style, and we have some extremities. Now, that's enough for the climbers. We also want to analyze the problems. For the problems, we approached it with a similar technique and ran PCA on them. And we see that these problems also are, the PCs are correlated with the probability of success or how difficult these problems are. We also see more structure to our graph, meaning that there are some factors that we have to actually examine more of. But unfortunately, we do not have the data exactly for analyzing direct paths and knowing how these exact paths differ, but that is an area to improve on. Next, how do we apply these?
Okay, so as we were talking about before, one thing that we get from the climber embeddings is basically a breakdown of both their success and I guess kind of like their style, right? And so if you're a coach or if you're just even a competitor, taking these breakdowns and looking at how good you perform across a bunch of different problems, you can kind of see where you excel and where you need improvements on different problems in their embeddings. In addition to that, we can think about route fairness. So we saw the video with Aimori and Yanya Gombre earlier, right? And you could argue that that's not necessarily like how you want to design your route if you're like the competition organizer and you're making the route itself, called a route setter. But yeah, so you might want to base it off of just their physical attributes, such as wingspan, like in that video. And so if you look at the problem embeddings components, you can kind of identify maybe where the shorter climbers perform better or where the taller climbers perform better and where the shorter climbers fall short. And by looking at the related problem embeddings, you can see, okay, maybe we shouldn't design a course that has this specific hold combination or something because that disadvantages someone's physical attributes. Whereas we might want to look at the different routes where they're more fair and rely more on the skill of the climber. So for next steps, we mentioned this a little bit before, but it would do wonders if we could expand our data set with like more information about things such as like how hard their grip strength is on a certain hold. So like having sensor data in that aspect, or things such as like their wingspan. You know, bouldering, it's like not a very obscure sport, but it's like not like the most popular thing ever. So even like scraping this data was very hard for us. So it would be cool if it was like more available, or if we can use this and incorporate it into our models. Furthermore, with the problem embeddings, it would be nice to be able to actually like visualize the problems, right? So if you're a administrator or a competition organizer, being able to use computer vision to kind of look at where the blocks are and identifying on a certain wall where the blocks are, as well as the paths that different climbers take, you can identify more or have a stronger analysis of which climbers are good at which different types of problems and where you can kind of design your routes to be more fair in that aspect. But yeah, we hope we've kind of shown you a little bit into the world of bouldering and competitive bouldering, and maybe even sparked your interest a little bit, as well as shown how good PMF is for giving us better insights with this seemingly, I guess, regular data. And yeah, we'd be happy to answer any questions you guys have.
Questions, both assume track. You'll just get questions from folks in the break time. So we're just gonna move on here to the next one. Grab that mic from you. Thank you so much, though. Excellent presentation. Switch over here now to our next group.